All right, I don't have very many sample papers because this is a paper that comes early in the semester, so most of the students collected their papers, but I had some here. So obviously you need a title, but the paper always begins with an abstract. Abstracts are really important because if you think about it, 90% of the readers that read your paper never make it beyond the abstract. Yeah. Most of the people, when they're doing their literature searches, they just read the abstract, and if it looks interesting, then they'll read the rest of the paper. And so a lot of people read a lot of abstracts and then use that. But the abstract should serve a purpose then, because it's going to be geared towards somebody not reading the entire paper. And so the abstract has to be like a spoiler. The abstract has to tell, you know, what the end result of the paper is, you know. And so it should be short. It should just be one paragraph, and basically it should tell you what you did and what you found. It's going to be the abstract. Let's see what this abstract reads like. A coordination compound is made up of a central metal ion to which other ligands are attached with. In the oxalate complex of potassium trisoxalate chromate 3 trihydrate, you know, and sometimes it helps to run the paper by other people to see if there's any errors. These papers, though, this semester were all individual, because I made everybody do it. You know, I don't like doing this one in groups because I want to see people's lab techniques, and usually the strongest person does all the experimental work. But so this was written alone. Since your papers are co-authored, you know, you have a group of people that can help you, you know, then the standards change a little bit. You know, I might have a little higher standard because of that. And so this is a totally individual report here. And so maybe I'm a little more lenient with individual reports. One person does all the work. The oxalate acts as a Lewis base by donating the free electrons in its structure to the metal that is the Lewis acid. For the preparation of this complex, the strong oxidizer dichromate reacts violently with oxalic acid. After the addition of the compound, potassium oxalate monohydrate, the mixture slowly produces deep blue crystals once it is cooled. Well, there's some, you know, details missing there, you know. Like, what are those deep blue crystals? Are those deep blue crystals the final product? Well, I guess you can infer that from the way it's written. So that's an example of one abstract. Let's look at another one here. Since this is the first paper for many of you, you know, I don't really grade this one so severely as we progress. Here's another one. Potassium, actually they start off with, it's fine to have chemical reactions in there, no problem. So you have some potassium dichromate plus some oxalic acid plus some potassium oxalate. I don't like it all grouped together though. You know, if you have two different reactions, you know, then I want to see two separate reactions. I don't want you to group it into one, like, okay, a redox followed by a Lewis acid base. I'd like to see the, I don't want to see them added up. I just want to see the redox first and then the acid base next, you know, in that sequence. But the book writes it like this, so a lot of people just copied it from the book. But, you know, you notice I didn't write it like the book. I'd like you to write it like I wrote it, right? Not like the book writes it. Preparation of oxalate containing coordination compound was the goal for this experiment. The synthesis, that formula there, calculating its theoretical yield and determining the percentage yield were the experimental goal. To a suspension of oxalic acid in 20 milliliters. You know, somebody who doesn't have much time, are they going to want to read this? You know, 20 milliliters of distilled water, all this stuff? Only if they're really interested, right? Only if they're actually going to synthesize it do they need the numbers. Most people that read your paper aren't actually going to synthesize it. A few will, so you need the synthetic method. You know, because a few will want to repeat it, especially if they don't believe you. It's like the arsenic bacteria. A lot of people tried to repeat that following the procedure that was written in there, but couldn't. And so go ahead and continue reading that. Let me just sign this. So nobody's going to want to read this. It's too much. This is good. It is green, black, bronze crystal. Okay, crystal, I don't know, is that one gigantic crystal or a whole bunch of little crystals? No. After determining the actual yield and theoretical yield, this is good too. They give us some numbers here. If calculating yield was part of this, then you should tell the reader that without having to make them read the whole paper to figure out what the yield is. Because some people are very curious about the yield, because some synthesis methods yield better results than others. Okay, here's another abstract. I could only find 3 papers. So these are the 3. These are not likely the 3 best, examples. The 3 best are probably collected. But anyway, the purpose of the experiment was to understand coordination compounds. K3, etc., was created in the lab through chemical reaction and filtration. That's kind of nice, chemical reactions we use. Reaction was made up of Lewis acid base, redox reactions, and metathesis reactions. Was there a metathesis reaction? Actually, I was a little bit wrong about one of those. In the crystallization step, what happened? It's formation of solid, but how are the solids forming? How is the solid? The ions are combining. Ion combinations are metathesis. So there is a metathesis reaction there. Because we just didn't evaporate. If we just evaporated, that's not really a metathesis. You're forcing the ions together, right? But there's plenty of liquid in there. And the only reason the precipitate came out was because the ions were attracted enough. In fact, they didn't really like being in ethanol. So they'd rather pair up than this. And so yes, there is a metathesis reaction. Potassium dichromate, oxalic acid, and potassium oxalate monohydrate were used in the process of making. This is good. That's simple. It tells us what they used, but it doesn't really give us all the details. But if we want all the details, we could read the paper. But we know it's involving metathesis, Lewis acid base, and redox, right? We could, you could make this a little bit longer and specify what the redox reaction is, what the metathesis, what the Lewis is. So that's fine too to make it a little longer.
Did you get points off for using Wikipedia as a reference?
No. Do you guys get points off in other classes for using Wikipedia? Wikipedia is, in a way, it's at least the science. Some of the science is just total garbage with Wikipedia, but a lot of it is reviewed. For example, a lot of the data. A lot of people use Wikipedia and they look at the data, and so the data is pretty good, I've found. And so it's not like a blog or something like that, or Yahoo Answers. Yahoo Answers, at least there's some review process in Wikipedia. Yahoo Answers, go look up naming. Oh, it's so funny. I was looking up a complex, and I saw that on Yahoo Answers, some student asked, "What's the name of this?" And then I read all the answers. All the answers were just way out there. And then the best answer, which everybody agreed, was way out there. I mean, it was awful. But it was kind of funny. I don't know if it was a joke or if it was real. But anyway, along with an intermediate step of filtration and ethanol wash, the resulting acid-base reaction was a combination of rock-like and sand-like dark blue chunks of crystals, which were purified and weighed out. So those are 3 examples of the abstract. Following the abstract comes the introduction. So let's just continue with this paper. Introductions, these don't have to be very long. Introduction is either this, or all of it combined. Some history, like who discovered this compound, etc., how was it synthesized? Or some notes about the technique that you're using, if there's a special technique that needs to be illustrated here. Or just general interest stuff. But usually introduction gives some historical background plus what's interesting about this. Why are you studying this? Who cares about this? Who cares about this oxalate complex? A lot of people don't care about this oxalate complex. Why do you care about it? Were you forced to do it? The Chem 1B instructor forced us to synthesize this oxalate complex. Or, does this oxalate complex have any value? Or is this just pure research? So those types of things you can talk about in the intro. And so, there's really no right or wrong answer for introduction section. Just whatever you want to write. And so let's read this. And Wikipedia is okay, but, don't copy and paste. A lot of people do that. They just copy and paste the Wikipedia entry into their paper. And then I check it and I see that's plagiarism. I have to give it F's for those papers. I'm supposed to give F's for plagiarized papers. Okay? So don't do that. If you do use Wikipedia, make sure you cite it, or make sure you put it single space or block it or change the font to show it's a quotation from there. Coordination compounds were a mystery well throughout the 18th and 19th centuries. So they're talking a little bit about the coordination complexes. That's good. It was not until the early 20th century when Alfred Werner in his study on metal-amine complexes, for example, that one, proved that coordination compounds are a very useful substance. Today, coordination compounds are used in a variety of applications. One such application is the use of coordination compounds as catalysts to speed up chemical reactions. In our experiment with coordination compounds, we used oxalate complexes and reacted them in order to familiarize ourselves with some of their physical and chemical properties. We really didn't do that, did we? We really didn't. Did you take the oxalate complex that you just synthesized and now you're going to subject that to different chemical reactions and measure its properties? No. And so that's a bit beyond what we did. In our work, the experiment consisted of a specific outline which we followed in order to complete the lab. Well, that last sentence you could omit. It doesn't really do anything for us. Let's check out this introduction. The coordination compound is important in understanding biological, environmental, and industrial applications. Okay, so here, I want to know why they're important. Reaction oxalic acid with a transition metal produces coordination. This one doesn't have too many. I didn't really deduct too much, although this paper, I can tell you the grade on this one. Other ones that don't have grades. Compounds of oxalate complexes, one of the most important properties of transition metals is their ability to form a lot of coordination compounds. Coordination compound involves all compound of transition elements where the transition metal is considered as Lewis acid, and the molecules that are attached to this metal are the Lewis bases. The joined molecules or atoms are called ligands, and when they're joined, they aren't called ligands. When they're joined, they're called complexes or coordination compounds. And the written formulas are denoted by square brackets for the solid, etc. Chromium-3 acting as the Lewis acid,
That would solve it. I do that all the time. I do that all the time. I go like, come on, wake up.
That was weird. Actually, I just remembered. It's not the computer. I'm using the document camera here. The document camera LED's gone off. All right, now it's coming back on. All right, and C2O4 ions acting as Lewis base. Chromium is one of the most familiar transition metals, are highly colored, and this is considered as a unique physical property. It's wrong. This physical property is common among all the transition metals in the first row because the 3D orbitals are not equal in energy. You know, for complexes, yes. When the d subshell is partially filled, an electron can be excited from the lower energy d orbitals to higher ones. This is the second half of chapter 24, so this is good. This person researched a little further on talking about the color. One on absorption of light from the visible region that causes highly colors in the coordination compounds containing transition metals. There's also a writing center too that you can bring your papers to, and they'll check it for you to make sure. And it's a free service, but I don't know how impactful it is to make it easier to read. The coordination covalent bonds in chromium-3 complexes are quite strong. Well, maybe that's a sign.
What grade did that paper get?
Well, this paper ended up getting a C+ because they're missing a lot. You know, this stuff, the abstract, the intro, and another section called the experimental, is not the most important part. The most important part of the paper is the discussion. And so even though they did a lot of writing for this and they did some research for this, the discussion was missing some key stuff that I was looking for. And so for your papers, and this is why you want to start with the discussion. The discussion is what you want to spend most of your time writing about. And
what's the average length of these papers? The average length of the papers?
The average length was about 5 pages. Let's see, 6 pages. This one was 6 pages. Well, make that 5 pages. 6 pages in one sentence. Usually I like single space like this. Let's see how long. Some were very long. This is 5 full pages here. Out of the 5 pages, this person had pictures too. Only 2 pages of discussion. You know, what am I looking for in the discussion? You know, people who don't write the equations, boom, you know, their points deducted. You know, people who don't talk about the reactions, a lot of people just combined all the reactions into one step. Remember I told you that the book writes it like this? Maybe you can guess why this person got the C, because that's how they discussed the chemical reaction. Do you see that equation up there? That was it for the discussion. You know, no talk about redox, that kind of stuff. Actually, they did talk some more. Let's read the discussion. Because the people who really don't talk about anything can get a D or an F on the paper, actually. Do you want to see a D paper or an F paper?
Yeah.
I have some examples of that for other reports. I don't have it for this one because this is all I got. I don't have an A paper for this, unfortunately. But there were some A papers, and I think that one of the papers I got for this was over 10 pages. You know, they did so much extra. You don't have to do it, you know, to get an A, but they did so much extra. They also talked about certain things that I was looking for, you know, that I mentioned already. All right, so this is working again. Do you want to keep going through these, or no? All right. Ready to? If you cite it in the paper, well, you could cite it in the paper as a name and then date or something like that, and then reference it. You could either do footnotes or endnotes. It depends on how detailed your citation is within the paper. You know. Actually, this one maybe. This one they did a lot. It must have been something else I saw here. No, I don't care about that. So let's just take a look at the results and discussion section here. Also, if you pull figures off the internet, make sure you cite them. Like this has no reference. And so also that's somebody else's work that you're copying. So you got to make sure you give proper credit for that. So that would lead to a deduction there. All right, this paper was very weak here. This is basically this is all they talked about for the chemical reaction here. So even though they did write 5 pages worth of stuff, you know, the discussion didn't talk about what we've outlined here. And so, and not only that, this discussion, we don't care about the amounts in the discussion. We want to know what's happening with the chemistry. The amounts actually go into a different section. So this paper was sub C. The amounts go into an experimental section. You know, the experimental details here. That's where you're going to get all the quantities. You know, 3.6 grams of potassium dichromate, the 250 milliliter beaker, 10 grams of this. You know. This is nice. You know, pictures of their crystals. They got nice crystals there. You see the facets of it, the faces. But they're repeating a lot of this here. 10.01 grams of oxalic acid. This is into a 250 milliliter beaker. This is not what I want to see in the discussion. So is that clear enough? I don't have to go through these again? You're not going to ask to see these? Not later. We're going to do it now, and then you get an idea, and then we'll do it. This is why you're going to turn in a rough draft, right? For this report. The rough draft, then I'll tell you what you need to do. But some people, when they turned in the rough draft, you know, the more stuff you have in the rough draft, the better. You know, some people turned in rough drafts that were just a few sentences last time I did this. All right, so that